In the context of special relativity, four vectors are a mathematical representation of physical quantities in four-dimensional space-time. They help to describe events, momentum, energy, and other properties of particles in a relativistic framework. The concept of four vectors in classical physics, we often deal with three-dimensional vectors such as position or velocity in space. However, in relativity, the need arises to work in a four-dimensional space-time where time is treated as a fourth dimension, and we combine it with the usual three spatial dimensions. Space-time. In special relativity, space-time is a unified structure consisting of three spatial dimensions x, y, z and one time dimension t. A four vector is a vector in this four-dimensional space-time. Common four vectors in special relativity. Four position, that is x upon mu. The four position vector describes the location of an event in space-time. It combines both space and time coordinates into one entity. It is defined at x superscript mu is equals to ct, x, y, z, where x mu is the four position with mu is equals to 0, 1, 2, 3. C is the speed of light, t is the time coordinate in the frame of reference, x, y, z are the spatial coordinates. The index mu runs from 0 to 3, with 0 corresponds to time multiplied by c to keep the units consistent with the space, and 1, 2, 3 corresponds to the three spatial dimensions. For velocity, u mu. The four velocity is the rate of change of the four position with respect to proper time tau, which is the time measured in the rest frame of the particle. The four velocity of a particle is defined as u mu is equals to dx mu d tau, that is gamma c comma v, where v vector is the component vx, vy, vz is the usual three velocity of the particle. Gamma equals to 1 upon root under 1 minus v square by c square is the Lorentz vector, c is the speed of light, and d tau is the proper time, the time measured by a clock moving with the particle. In components, this is u mu equals to gamma c comma gamma v. The four velocity always has a magnitude of c square in the space-time metric, that is u mu superscript u mu subscript is equals to c square regardless of the particle's position. Four momentum. The four momentum is the relativistic expression of the classical momentum. It combines the energy and momentum of a particle into a single four vector. It is defined as p superscript mu is equals to mu superscript mu equals to e by c comma p, where m is the rest mass of the particle, u mu is the four velocity, e is the total energy of the particle, that is gamma mc square, p vector is the three momentum, that is gamma mv. The energy and momentum of a particle are encapsulated in this single four vector. Four force, that is F superscript mu. The four force is the relativistic version of force defined as the rate of change of four momentum with respect to the proper time. F mu is equals to dp mu superscript over d tau. It relates the force acting on a particle to its motion through space-time. Four acceleration, a mu. The four acceleration is the rate of change of the four velocity with respect to the proper time. A mu is equals to du mu d tau. This represents how the particle's four velocity changes as it moves through space-time. Minkowski inner product. In special relativity, we work in a Minkowski space-time with a metric tensor that differs from the Euclidean dot product. The Minkowski inner product between two four vectors a mu and b mu is a mu superscript b mu subscript is equals to minus a naught b naught plus a dot b vector, where a naught and b naught are the time components multiplied by c, a vector and b vector are the spatial components. Note that the time component has a negative sign. In some conventions, it might be the opposite with the spatial moments components negative. This gives the space-time structure where the distance between events can be positive, 0 or negative depending on the metric.